The next thing we're going to look at is differential equations. And so in this little demonstration, we're going to talk a little bit about what it means to be a solution to a differential equation, and then what information can you extract from them. So a solution is just an equation that will make a differential equation true. And in your reading, you should have seen that a differential equation will involve the value x, y, and then some derivatives, maybe y prime, y double prime, or several more derivatives even. So let's just look at an example. We're going to want to show that the function sine of 3x is a solution to the second derivative of y equals negative 9 times y. The way we do this is we look at both sides of the equation. So we've got the second derivative on the left side, negative 9y on the right side, and we figure out what each of those are. So let's look at the second derivative of y with respect to x. So we're going to take the derivative of the sine. The derivative of the sine is 3 times the cosine of 3x. Now we need the second derivative, so we have to take the derivative of this again. The derivative of the cosine of 3x is the opposite of the sine of 3x times another factor of 3, which will give us negative 9 times the sine of 3x. Okay. So now we hold on to that. We go back to negative 9y, figure out what it will be equal to, and then compare the two. So negative 9 times y we said was equal to the sine of 3x, so negative 9 times y becomes negative 9 times the sine of 3x, which, when we compare these two, are equal. And so therefore, y equals the sine of 3x is a solution to that particular differential equation. Okay. So what else can we do with differential equations? Well, we can look at differential equations and read information off about the function to get an idea of what's going to happen. So this is just a quick little example. Newton's law of cooling will tell us that if I want to figure out how quickly a quantity's temperature is changing, that is, an object's temperature is changing, I need to look at the difference between the temperature of the object and the temperature of its surroundings. And the rate is proportional to that difference. Okay, so for instance, if you are out on a 95-degree day and you have an ice cube, throw it outside, well, there's a great difference between the temperature of the ice cube and the temperature outside. And so at the beginning, the rate at which the temperature of the water in the ice cube is changing is very fast, or the rate is very high. On the other hand, if it's a nice spring day, but a little bit rainy, so it's not a nice spring day, I guess, instead, the temperature outside is about 40, and so you throw an ice cube out there, and yes, it's going to adapt to the temperature outside, but at the beginning, the rate at which it's changing is not going to be as great. So the equation that we get from this, and some of these will be given to you here, is dt, that's the rate at which the temperature is changing, is proportional to means we'll get a constant multiple. That's what the k is. The difference between the temperature of its surroundings and the temperature of the object. Now P here represents the temperature of the surroundings, and T is the temperature of the object. And here we'll just assume that K is positive. So let's just ask a very simple question. What happens if P is greater than T? What happens if P is less than T? And we'll look at them both from the setting of the equation and then from a practical setting. What does this really mean? Okay, so we'll just focus on what happens if P is greater than T. If P is greater than T, then P minus T is going to be positive. Well, P minus T is positive. We multiply K by K is a positive number, so we multiply two positives, so we get a positive, which means that the rate is positive. Well, if the rate is positive, then the function is increasing. The function here is T, so the temperature is increasing. Does that make sense? Of course it makes sense. If the surroundings are warmer than the object that we have, our object is going to warm up. Okay, take a hot oven, throw in a baked potato. Well, it's not baked until we put it into the oven and let it sit there for a while, but throw a potato in, and the temperature of the potato will rise. You can also do the same thing. What if P is less than T? Well, then the difference is going to be negative, and therefore the rate is going to be negative. It will be decreasing. We can also verify once again that if p and t are very far from each other, the rate will be very large because that difference will be large.